Wonderful to see everybody. This is going to be a really interesting presentation on graph theory. Very, very useful, very valuable knowledge in this presentation today. So I think we're getting ready to set to go. Rabia Liaquat, I'm looking for you. There you are. I'm going to move you up where I can see.
Hello, how are you?
I'm good. How are you today?
I'm fine.
How's the weather there?
It's good.
Nice.
Yes.
Well, I think we should get up and start because we're a little late.
Yes.
So tell us your name, where you're from, and a little bit about your background.
Hello, my name is Rabia Liaquat and I am PhD student in mathematics. My area of research is graph theory. Now I am studying graph theory, the topic.
So do you have a presentation to show us?
Yes.
Okay, I think you should have the permission to start your presentation. You just have to share it from your computer screen.
Okay. Let me share.
Do you see the link down below and like a little green button for share screen?
Okay.
And it looks as though you have permissions. Yes. You have permission to start your presentation.
Okay. Give me 2 minutes.
Okay. Yeah, you'll have to open up your presentation in your computer, and then you can grab it. Okay, perfect. So graph theory, mathematics.
Yes.
So we're going to learn what is graph theory, and then how to apply it to your research and how to apply it to your work.
Yes. Graph theory is basically the relationship or connection between 2 points, vertices. These are called vertices. Can you see my screen?
Yes.
Okay. So first of all, overview of the last lecture is introduction. What is introduction of graph theory? Graph theory is basically, connection between points and relationship between points. Points may be any place, any persons, cities, anything according to the situations. So for example, we have points and we can draw any relationship between points according to the situations. This is the basically the purpose of graph theory is to describe the relationships. Okay. In the last lecture, we discussed about the introduction, degree of vertex. What is the degree of vertex? For example, we have vertices A, B, C, and D. So A, B, C, D are the vertices, and the relationship between A and B can be drawn a line which is called edge. Okay. So degree of vertex, the degree of vertex is A, is 3. Because there are 3 edges belongs to A. So in the last lecture, we discussed the types of graphs where we discussed null graph, which is a graph which is nothing, no any vertex or no any edge. This is a null graph. Then trivial graph, which has only one vertex. This is a trivial graph. Then cycle graph. Cycle graph is a graph where we can discuss if we have a point A, we start from A to B and then again back to A. Then this is a cycle graph. Initial and end point is same. Then this will be a cycle graph. Undirected graph where there is no mention of any arrow. For example, this is a undirected graph. And then directed graph, for example, if we have arrow from A to C, there is an edge A to C, there is an edge from D to A, and an direction A to B. So this is a directed graph. Then simple graph is just this one, where there is no any cycle exist. For example, A, B, C, this is a graph. This is a simple graph. No multiple edges and no exist of any loop. Then multiple graph, multi-graph is a graph where multi edges can exist from one vertex to another vertex. For example, this is two vertex, one edge is this and back to the same vertex. This is multiple graph. Connected graph is simple, any graph which is connected. For example, this is a connected graph, and if there is any any vertex is here, if we remove this one edge like this one, so this is now a disconnected graph because there is an two graphs. So disconnected graph, then planar graph. Wait. Planar graph is the graph which we can draw in a plane. In other words, there is no any intersection between two edges. For example, this is not planar graph because there is an intersection. There is an intersection of two edges, so this is not a planar graph. If there is no any cross between any two edges, then this is a planar graph, right? What? Understand? So next is complete graph. Complete graph is something, for example, we have vertices, four vertices. So one vertex will connect every vertex. Similarly, the second one vertex will be connect to every vertex. Similarly, third one vertex will be connected to every vertex, each and every vertex. Similarly, fourth vertex will be connected to every vertex. So this is complete graph, right? Next, adjacent vertices and edges. What is adjacent vertices? For example, we have vertices, we have a graph like this. A, B, C, and D. So A and B are adjacent vertices because very next vertex is B and both are connected. Similarly, A and C are not adjacent vertices because there is no any relationship between A and C, and A and D is no adjacent vertices because there is no any edge between A and D. But B and C are adjacent vertices. Similarly, C and D are adjacent vertices. Now edge, what is the adjacent edge? AB, this is an edge and this is an edge. Both are adjacent edges because AB and BC both are connected, right, through a vertex B. So this is adjacent edge. Similarly, CD and BC both are adjacent edges. Handshaking lemma. What is handshaking lemma? In the last lecture, we studied about the handshaking lemma, which is 2E equals to sum of degree sequence. For example, we have this graph. So 2E means edges. So how many edges here? 1, 2, 3, 4, 5, and 6. Means we have 6 edges, which is equals to sum of degree sequence. Sum of degree sequence means for example, we name this A, B, C, and D. Degree sequence of A are 3 because there are 3 edges passing from A. 1, 2, 3. So degree sequence 3. Degree sequence of B is also 3. Degree sequence of D is also 3. And degree sequence of C is also 3. So 3. And for example, this is also an edge. We named it F. So 1, 2, 3, 4. 4 edges here. 4-degree sequence here. So 3 plus 3 plus 3 plus 3 plus 4. So this is hand-checking lemma. 2 multiply number of edges is equal to sum of degree sequence. Next, we will talk about trees. What is trees? Trees is just a simple path where this is a tree. No loops, no multiple edges, no making of any cycle. Trees is just like a path between any two vertices. For example, this is a tree. Just like this. No multiple edges, no loops, no closed path. So Euler graph, today's our main topic is Euler graph and Hamiltonian graph. Okay, and the Dijkstra algorithm in the last lecture we read a algorithm which calculate the shortest path. So our main focused is Euler's graph and Hamiltonian graph. So let's move. What is Euler graph and Hamiltonian graph? Euler graph contains a cycle that includes every edge only once, and similarly Hamiltonian graph consists a cycle that includes every vertex only once. And we have two theorems which we apply today. Sorry. Okay. We will apply two theorems, and with these help we will calculate Euler graph and Hamiltonian graph. First result is a connected graph is Eulerian if and only if each vertex has even degree. Even degree means, even degree means, for example, we have a graph A, B, C, and D with 4 vertices A, B, C, and D. For example, A has a vertex. A is a vertex with 2 edges, so degree is 2. B is a vertex with 2 edges, so degree is 2. Means even degree sequence. And second one condition for the Hamiltonian result is let G be a simple connected graph, means no cycle, no loop. So let G be a simple. This is a simple graph. No multiple edges, no loop exists in simple graph. So for example, we have a graph. So let's suppose A, B, C, and D. This is the graph. Simple connected graph with n vertices. For n vertices means n should be, this is a condition for n should be greater or equals to 3. For example, n should be start from 3, 4, maybe 5 vertices, maybe 6, up to so on. And degree of V plus degree of W is greater or equals to n. This will be the condition which will be satisfied in Hamiltonian graph. For each pair of non-adjacent vertices, what is V and what is W? That should be non-adjacent. For example, A and D. This condition will be A and D because both are non-adjacent vertices. Because there is no any relationship between A and B, or there is no any connection between A and D. So V and W are non-adjacent vertices, and we will calculate the degree of V. For example, degree of A is 2 and degree of W is means degree of D is 2. We will add both. That will be should be equals to greater or equals to n. What is n? N will be number of vertices. 1, 2, 3, 4. 4. means 4 is equals to 4. Satisfy. Okay. This is the result for Euler graph. This is the result for Hamiltonian graph. So next we will let me show some examples of Hamiltonian graph and Euler graph. For example, I have a graph. Let me draw a graph. Oh shit. Now this is a graph. We want to calculate, is it Eulerian graph or Hamiltonian graph? Understand? So we will apply these conditions and will calculate the Eulerian graph or Hamiltonian graph. First of all, for the Eulerian, a connected graph is Eulerian if and only if each vertex has even degree. So, for example, we have 1, 2, 3, 4, 5, 6, 7. 7 vertices, which are A, B, C, D, E, F, and G. These are 7 vertices. We will calculate degree sequence of each vertex. For example, A has degree sequence 2, 1, and 2. 2 edges passing from A, so 2. Degree sequence of B is 1, 2, 3, 4. There are 4 edges coming from B. So B4. How many degree sequence of C? Anyone can tell? Yes, 4. What is the degree sequence of D? 2. What is the degree sequence of E? 1, 2, 3, 4. Degree sequence of F? 4. Degree sequence of G? 4. So every vertex has degree sequence even. So this is a Euler graph. This is a Euler graph. So now we will check, is it an Hamiltonian graph? For example, we have 7 vertices, means n is equals to 7. What was the condition? Degree of u plus degree of v is greater or equals to n, where u and v are non-adjacent vertices. For example, we can check this condition for A and E. For example, we check for A and E. Degree sequence of A is equals to 2. Degree sequence of E equals to 1, 2, 3, 4. 4. So 2 plus 4 is greater or equals to what is n? 7. Now we will check about, for example, we have a vertex A and vertex T, or vertex B and vertex E. Both are non-adjacent vertices. Let's check. Degree sequence of B is equals to 1, 2, 3, 4. Similarly, degree sequence of E is equals to 1, 2, 3, 4. So degree sequence of B plus degree sequence of E equals to is greater or equals to 7. For example, 1, 2, 3, 4, 4 plus 4. So 8 is greater than 7. So it satisfies. So this is Hamiltonian graph as well. Let me draw a path for Eulerian graph and Hamiltonian graph. Due to both these results, we just see that is it a Eulerian or Hamiltonian graph, yes or no. Now we will draw a path of Eulerian graph and Hamiltonian graph, where Eulerian graph tells us contains a cycle that includes every edge only once, and Hamiltonian said us includes every vertex only once. That we can see A to B, for example, B, C, D. A to B, B to C, C to D, D to E, E to C, C to G, G to E, E to F, F to G, G to B, B to F, and F to A. You can clearly see that every edge is comes only once. So this is Eulerian graph. Next we see A to B, B to C, C to D, D to E, E to G, G to F, F to uh, sorry, E to F, G, G to F, F to B, sorry, F to E. So this is a Eulerian graph. Now we can see vertices. Let's move from A to B, B to C, C to D, D to E, E to G, G to F, F to A. Every vertex come only one, and there is no repeat of vertices. So this is Eulerian graph as well. Understand? Okay. Any question? Let me show you another example. B, C. So is it Eulerian and Hamiltonian? Let me check. Degree sequence 2, degree sequence 2, degree sequence 4, degree sequence 2, degree sequence 2. Every vertex has even degree sequence, so this is Eulerian graph. Let me draw a path B to C. Yes, every edge exactly comes one, and there is no any repetition of edge. And we cover all the graphs. So this is Hamiltonian graph. sorry, Eulerian graph. Now we will check Hamiltonian graph. For example, I choose B and F because both are non-adjacent vertices B and F. We will check the degree. Degree of B is 2. Degree of F is also 2. Okay. Now degree of B plus degree of F should be greater or equals to N, means but how many vertices? 1, 2, 3, 4, 5. So degree sequence 2 plus 2. So this is not a Hamiltonian graph, but this is Eulerian graph, right? Now please note down these examples. Let me show one example which is a Hamiltonian graph but not Eulerian graph. G. So this is Eulerian graph, not Eulerian graph. Why? Degree sequence 3. Degree sequence 3, 3, 3, 4. So degree sequence are odd. So we can say this is not Eulerian graph. Now, how many vertices here? 1, 2, 3, 4, 5. Means n is equals to 5. So, and non-adjacent vertices. Degree, for example, this one, I choose B and E. Degree sequence of B plus degree sequence of E should be greater or equals to 5. So, 3 plus 3 is greater than 5. Satisfy? So, this is Hamiltonian graph but not Eulerian graph. And the last example is which is neither Eulerian graph nor Hamiltonian graph. So, A, okay. This is let me check degree sequence 1, 3, 3, 4, 1, 1, 2, 3, 4 or 4. So degree sequence odd. So not Eulerian graph. Now non-adjacent vertices B and E. Let me choose B and E. Degree sequence of B is equals to 3. Degree sequence of E equals to 4. So degree sequence of B plus degree sequence of E should be greater or equals to N. What is N? How many vertices? 1, 2, 3, 4, 5, 6, 7. Okay. Three plus 4, 7. Satisfy? Let me choose another one. For example, I choose A and D. Degree sequence of A is 1. Degree sequence of D is 1, which is equals to 2, but which is not greater or equals to 7. So not satisfy. So this is not neither Hamiltonian nor Eulerian. Understand? Understand? Next is an application of Eulerian graph. Eulerian graph is we can solve a problem through Eulerian graph. First of all, this is a real life problem, Domino's game. Let me start from Domino's game. What is Domino's game? Actually, Domino's game is a family of tile-based games played with. Dominoes is a family of tile-based games played with gaming pieces, commonly known as dominoes. Each domino is a rectangular tile like this. This is a rectangular tile, usually with the line dividing, and there is a line which divides the rectangle, its faces into two square. When we divide a rectangle, we get two squares, 1 and 1. Okay. Each with two squares ends, each square marked with the number of dots. Each square marked with the number of dots. For example, dots in a dice. 1, 2, 3, 4, 5, and 6. Or it will be a empty here. So number of each square marked with the number of dots, also called pips or dots, or is blank. The gaming piece make up a domino set, sometimes called a deck or pair. It consists of 28 tiles. Our aims in here, our aim is connect the same number of dot squares. For example, we have a tile with this one. Next player will attach another tile like this one. Sorry. For example, one player places a tile this. Next player will check their tiles and will place a tile next to the this one, which should be 2. Sorry. Attach 2 with 2. For example, next player has tile this. So first one player will attach either the first one player should place his tile like this one. If he has 5 dots in his tile, then he will attach the same. Similarly, this one same. Similarly, we can get a chain of tiles, and this game we can play. Now, I will explain how Eulerian graph can be used in this one. For example, this one, this image, a player can play a game where this one tile next player will attach 4 with 4, and then next player attach 1 with 1, 5 with 5, 6 with 6. Now, how can Eulerian graph apply here? For example, I take a graph with K7. K7 is a complete graph with 7 vertices. So let me write here. Zero, 1, 2, 3, 4, 5, 6. So 0, I named each vertex 0, 1, 2, 3, 4, 5, 6. First of all, I will take edges from 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6. Let me write here 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6. Okay. Let us label the vertices 0, 1, 2, 3, 4, 5, 6 consecutively. Then an Eulerian trail or Eulerian graph is obtained by tracing the edges in the following order. In the following order, we can make edges 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6. Next, 0, 5, 6, 5, 6, then 6, 0. Next is 0, 0, 2, because we come from 0, 1, 1, 2, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 0. Next we will move towards 2, not 1, because already we covered this edge. So next one is moving from 0 to 2, 2 to 4, 4 to 4 to 6, 4 to, sorry, 2 to 4, 4 to 6, 6 to 1. Right? Means I come from 0 to 2, 4, 4, 6, 6, 1, 1, 3. Now I will move from 1 to 3. I cannot go 1 to 2 because already covered. So 1 to 3, 3 to 5, 1 to 3, sorry, 1 to 3, 3 to 6, sorry, 1 to 3, 3 to 5, 5 to 0, and 0 to 3. Next, I will move from 2 to 5, 5 to 1, 1 to 4, and 4 to 0. like this one. Mm, 6, 25, 51, 14 and 40. So here we can cover every edge with no repetition of an edge. So this is Eulerian graph. Let me tell you again, how can I move? So I start from 0, 0 to 1, 1 to 2, 2 to 3, 4, 4 to 6, 5, 5 to 6, 6 to 0. Then I move from 0 to 2, 2 to 4, 4 to 6, 6 to 1. Then I will move from 1 to 3, 3 to 6, 6 to 2, and then 2 to 5, 5 to 1, and 1 to 4, 4 to 0. And I cover all edges only once. So this is a Eulerian graph. When we follow this one, so tiles of dominoes, these, how I 0 1 0 1, this one, 0 1 1 2 2 3 2 3 3 4 3 4. So I place all tiles like this. So this is an application of Eulerian graph which we use in dominoes game and place all tiles like this one. Next, problem related Hamiltonian cycle. So imagine yourself to be the Vasco da Gama of the 21st century who have come to India for the first time. Now you want to visit all the World Heritage sites and return to the starting landmark, but then there is a budget constraint and you don't want your crew to repeat site. Seems pretty tough for a young explorer, right? These situations can be imagined as a classical graph theory problem where each heritage site is a vertex and the route from one side to the other is an edge. This route map of visiting every node and returning to the starting node is what called a Hamiltonian cycle. For example, I have a graph like this one. So these are World Heritage sites from let me label it A, B, C, D, E, F, G, and H, right? So I want to visit every site, but there is I want to visit every site, but due to shortage of budget, I want to find the shortest route where every edge, where every vertex will come, but every edge may or may not become. So this is the application of Hamiltonian graph. So every edge should be covered. So let me move from A to B, B to C, C to D, D to E, E to F, F to G, G to H, H to A. So these two edges are extra. So I cover from all vertices and cover all places. So this is the application of Hamiltonian graph where I visit every vertex only once, right? Understand? Now next, let's move towards the other topic, which is circulation demand problem. There are some factories that this is also real life problem. So circulation demand problem. There are some factories that produce goods and some villages where the goods have to be delivered. They are connected by a networks of roads, with each road having a capacity C for maximum goods that can flow through it. The problem is to find if there is a circulation that satisfies the demand. This problem can be transformed into a maximum flow problem. Add a source node S and add edges from it to every factory node F with capacity Pi, where Pi is the production rate of factory Fi. Add a sink node T and add edges from all villages Vi to T with capacity Di, where Di is the demand rate of village Vi. Let G is equals to Ve, where V is the vertex set. Let me write vertex set and E is edge set. With this new network, there exists circulation that satisfies the demand if and only if maximum flow value G equals to summation I belongs to V di. If there exists a circulation, looking at the maximum flow solution would give the answer as to how much goods have to be sent on a particular road for satisfying the demands. Let me let me do a problem related this one. This is the scenario of the problem. So okay, so let me draw a graph. Kindly draw this graph. Seven, 5, 10, 10, 1, 3, 2, 3, 7. This is maximal flow problem. So this is a graph. We want to find the flow from 1 to 7. So S is source and 7 is sink. Source means where every edge outgoing. From 7 and 10. These are outgoing edges from vertex 1. So this is source, and here where that vertex where every edge enter, this will be sink. So first we will make the same graph as it is. Let me draw. So I will write these length like this one.
Rabia, there is a question in chat. Can I ask you?
Yes, please.
It's from Rosendo. How is the best practice to stabilize the way or order of each number?
Yes, kindly repeat your question.
Yeah, what is the best way to stabilize the order of each number?
Order in each number.
Do you understand the question?
No, sorry.
Yeah, so it's like, of course, we need to have a very clear, we need to be very clear with the process of the number of ordering the numbers.
Yes.
But is there a best way to order the numbers?
Order the numbers.
Yeah.
From this graph, okay, this problem is given. and order is already given to you. And this data come from the problems where who want to solve this one. So here is a problem. First we draw as it is and write like this one. Why we write this one? First of all, what is over and 7? For example, we have 3 by 5. Here is capacity and here is flow. So first of all, we want to move from 1 to 7. There are two paths from going 1 to 7. One is from 1 to 2, 2 to 5, 5 to 7. Second one is 1 to 3, 3 to 6, 6 to 7. So let me write path. One to 5. Sorry, 1 to 2, 2 to 5, 5 to 7. What will be the flow? First of all, 1 to 2, 2 to 5, 5 to 7. What is the shortest capacity from 1 to 2, 2 to 5, 5 to 7? The shortest capacity is 5. So 5 minus 5, we will write here 0. 10 minus 5, 5. And 7 minus 5 is 2. Right? So here flow is 5. We can write his, because shortest capacity is 5. So we choose the shortest capacity, which is 5. Next route is, and here this will be blocked. So second path is 1 to 3, 3 to 6, 6 to 7. So the shortest capacity here, what will be the shortest capacity here? Anyone can suggest what is the shortest capacity, 10, 7 or 4? Yes, 4. So
The
4
student,
minus 4.
the student
Yes,
who answered that question, Tanjavel,
yes.
would actually like your email because he is a mathematics student. And so he would like to be able to contact you after the presentation to help with his
Yes.
mathematics. Would you be able to do that?
Okay, let me write here in my email. Receive.
I do not see it yet.
Right here.
Oh, on the whiteboard.
Yes.
Liaquat, Rabia,
Yes.
9082 at Gmail.
.com. Okay.
Thank you very much.
Welcome. So the shortest capacity is 4. 4 minus 4, 0. 7 minus 4, 3. 10 minus 4, 6. So where I got 0, that will be blocked. So the flow is 4. Now the next route is from 1 to 2. We cannot go 5 because this is blocked. We can go 1 to 2, 2 to 4 or 2 to 3. Let me go 1 to 2, 2 to 4 and 4 to 5, 5 to 7. So what is the shortest capacity? 1 to 2, 2 to 4, 4 to 5, 5 to 7. The shortest capacity here is 2. This is 2. So 0, 3 minus 2, 1, 3 minus 2, 1. And then this one, 5 to 7. Means 5 minus 2, 3. So this will be blocked because here 0 come. So the here flow is 2. The next path is 1 to, now the only path is 1 to 3. We cannot go to towards 2 because arrow is downward. So 1 to 3, 3 to 4, 4 to 5 or 6. And we cannot go from here because here is blocked area. So 1 to 3, 3 to 4, 4 to 5 and 5 to 7. 1 to 3, 3 to 4, 4 to 5 and 5 to 7. So what is the shortest capacity from 1 to 3, 3 to 4, 4 to 5 and 5 to 7 is 1. Shortest capacity is 1. So here is 0. 2 minus 1, 1. 6 minus 1, 5. And 3 minus 1 is 2. So here flow is 1. Here is blocked. So every route here is covered. Now we cannot go from 1 to 7 because every area is covered. So we get the flows 5, 4, 2, 1. At the end we will add them. 5 plus 4, 9. 9 plus 2, 11. 11 plus 1, 12. So maximal flow is 12. Right? Which is an application of, let me share you. Now read this carefully. We solved this related problem. There are some factories that produces goods and some villages where the goods have to be delivered. They are connected by a networks of road with each road having a capacity C, where C is capacity. C means we discussed about like this one. Let me draw first. So these are the capacities 7, 5, I think 10. These are capacities. So if there is a having a capacity C for maximum goods that can flow through it, the problem is to find if there is a circulation that satisfies the demand. So at the source node was this one, and the sink node is this one, 7. So this is the maximum flow value, which was 12, I think. We calculated 12. So this is the scenario, and here I draw the problem. So here I covered all topics today lecture. Any questions? Any question?
Do we have any questions? Do we have any
Yes.
questions? Ask about how you could use it. What are you studying? How could you use graph theory in your own research?
Okay.
Or
I
how can you contact an expert in graph theory and use their knowledge to help you in your research too?
okay. First of all, I search in the internet what is the open problems from the other researchers. Then I pick one of them and research on it by using my by using the knowledge of my professors uh, and research on the internet, Google, YouTube.
Well, let me ask you, Rabia,
Yes.
how do you apply the knowledge of graph theory? Do you have a particular area of interest?
Yes, I usually working on color labeling where we can solve. Let me, for example, uh, I have a Sudoku game. In Sudoku game, here will be we have blocks where we solve this like only one. There is not any repetition of numbers. So 1, 2, 3, 4. No repetition of number, but every block should a unique number. So we can use graph theory in this one, and in other fields where we can find the shortest route in Google Maps. Google Maps where we want to find the shortest route, and transportation area, and many other fields we can use graph theory. In factories where chemicals etc, the relationship between them, how many chemical will be used in to make any product, etc.
I don't know if anybody else can see it, but I see a big square blocking what you just wrote. I don't know how you can get rid of that.
Okay, let me explain you.
Okay. You know, also think about the ecology, where you have an ecosystem of different animals, predators and predators, and the prey of those predators, and the food chain and how it's all connected. So you draw a graph theory of these connections between different animals and how they're feeding upon each other. And then think about one of those animals going extinct for some reason. How will that affect the flow of food, the food chain with the other animals? Graph theory helps us understand that. These are very important questions that need to be answered about the world when certain animals go extinct? How will that affect the ecosystem? Will other animals then become extinct? And so by being able to graph the ecosystem and the food chain or where they're living, habitat, and then seeing disruptions in that ecosystem, then you can predict what's going to happen and then prepare for that. We have a question from Charles Zimba. Go ahead with your question. Let me go ahead and ask you to unmute. Go ahead and unmute, Charles Zimba. Are you able to?
Yes.
Charles Zimba?
Yes, I've managed to unmute.
Okay, go ahead with your question.
My question was actually overtaken, but I can still ask another one. And the other of sending a recorded version of this class. Or this online session.
Do you want the
If
recording?
the answer is yes, a recorded version.
We are recording this session. And
Yes,
so
are you able to send the feedback of the version to us again later so that we can continue listening to it until after some time?
Well, the recording of this presentation will be on YouTube within a few days on the AIU YouTube channel.
Okay,
So,
okay, that's fine.
So if you need the recording, you can always download it from YouTube.
Okay, that's good. That's okay. That was the primary question I thought I need to answer out.
Yeah, this is in a certain way, this is advanced mathematics, but it doesn't have to be advanced. Anybody can use it. You learn some of the concepts of graph theory, and then you're able to apply it.
It's very true, because like certain economies, their performances, we can create a graph theory for them, especially over a particular financial year. We can use the graphic theory very well, because the performance can never be at the same level when it is in a particular financial year. So the graphic theory is quite good. And
Yeah, think of optimization. Graph theory is used for optimizing situations, supplies, production, many things. Rabia, we have a question from Victor Hugo. How is this theory represented in equipment maintenance? Equipment maintenance.
Equipment maintenance. Okay. Actually, we used it on basically we used it in the games. Not I don't know. I don't think so. In equipments, we use it in management of games, tricks, rules, etc.
There's also a question, can graph theory be useful in environmental management?
Yes, environmental management. We can draw a relationship between two things. In environment, everything has a relation. Like predators, prey. There are also a relationship between them in ecosystem, environmental sciences. Everywhere relation should be exist. So I think yes.
We have another question from 326039. Oh, I don't know if I can unmute you. Are you able to?
Yes,
Do you have
yes.
a microphone?
Yes.
326039. Are you able to speak? I don't see that you have a microphone connected to Zoom here. 326039, go ahead and write your question in chat because you don't have a microphone connected to Zoom. A question from Rosendo. Do you recommend any software for graph theory?
Actually, initially we don't use any software. If we're working with the lots of relationships, then we usually use latex or R program. In data science, we use softwares, R program and MATLAB.
I have a question. What is the
Yes,
difference between graph theory and Venn diagrams?
graph theory and
Venn diagrams, VENN, where you
okay,
see
Venn
the
diagrams,
flow.
Venn diagrams. Okay, okay. I can like Venn diagrams, this one, and graphs are points and their relationships.
Yes,
This is a graph.
kind of like the flow chart. It's like a flow chart.
Yes. Flow chart, like this is a graph where we can make relations, connections. Here is Venn diagram where also relation, connections, or according, for example, this A intersection B is common area. A union B is, this is also a relation. Understand?
So graph theory mainly focuses in on points and not so much
Yes, points
areas.
and the relationships. Actually, these are all connected, but representations are slightly different. Different.
Can a Venn diagram be represented through graph theory through using points?
Actually, this is a set theory where we deals numbers, only numbers. But in graph theory, we deals everything. For example, person to person varies. From, for example, cities to cities. But in Venn diagram, we deal with sets. For example, one numbers, set of fruits, set of vegetables, etc., etc. But slightly difference in representation, but overall we can relate them. Graph theory, Venn diagram, flow charts, etc.
Okay,
Yes,
are you,
graph theory can also help us to transportation activities. Obviously, yes. We can find shortest path through graph theory. For example, let me show you an example. For example, we have a graph like this one. A, B, C, D, E. Okay, okay. If we move from A to B, A to E, for example, there is a 2, length 3, length 10, length 5, length 6, and length 1. For example, if we move from A to E, so we can move from A to B, B to D, and D to E. This is the shortest path. 2 plus 3 plus 5 equals to 11. Sorry, 10. And when we move from 10 A to B, D to E, means to say 10 plus 5 is equals to 15. So we will choose this one path. So we will go from A to B, B to D, D to E. Like just like to follow Google Map. So we can from A to B, B to D, D to E. This is the shortest path from where we can move A to E. Yes, all. Moving of materials, yes. Transportation models, supply chain movements, yes. We can use graph theory. Any other question?
If there are no more questions, we will go ahead and conclude this presentation on graph theory. Many of you probably are not familiar with graph theory, but now you are, to realize the power of graph theory to analyze connections, relationships, flows of different minerals, communications, information, electrical circuits. The use of graph theory is powerful in many, many things. And so I think Rabia Liaquat is just opening up this issue, this topic for a lot of you, and letting you see what it is, but you're going to have to get into it and learn its language. And once you learn the language of graph theory, you'll see how powerful it is to use as a tool for analysis. Here, like Emmanuel says here, any link with critical path analysis. Critical path for computing duration of work. Go ahead, Rabia.
Yes. Okay, let me suggest you a book. Wait.
So Wilson J.
Yes.
Maybe
Robin J. Robin
write
J.
it into, maybe I could write it into chat. I might even be able to find that book available on the internet.
Robin J. Wilson, this is the introduction to graph theory. This is the book where you can see the topic.
Is that Robin J. Wilson?
Yes.
I see the book on the internet. It's available in PDF.
Yes. Yes, available.
I see the 4th edition available. It's too big for me to load it into the chat in Zoom, though. And Paul Onyet, graphics can be used in advertising and markets, making attraction to customers, in education to explain the complex things, and also can be used in design and layout of many websites, magazines, and brochures. Yeah, graph theory is amazing.
Yes.
It's even the brain, the way the brain functions as far as connections between neurons and brain centers is graph theory. And so the brain, if there's damage to the brain can figure out different pathways through the nervous system to keep the body alive. And that's just graph theory, showing the connections between different areas of the nervous system.
Yes.
Okay, so I think if that is no more questions, we will go ahead and thank Rabia Liaquat for her presentation on graph theory. Thank you so much. Is there anything more you would like to say? Rabia Liaquat, anything more you would like to say?
No, thanks.
So you have her email if you want to learn
Yes.
more, if you have questions,
Yes.
and she can provide you with more information, answer your questions. And I think that'll do it.
Yes.
Thank you, everybody. And so my name's Dr. Edward Lambert, Academic Dean at AIU. This has been fascinating. I think many of you thought, graph theory, how can I use that? And maybe it's like statistics, where it's like, how do I use this? But once you see it, once you kind of start to talk the language, it's like the mind opens up to a different way of analyzing issues. So we want to leave you with a powerful concept of graph theory. And Rabia Liaquat has done a great job of showing you connections, different types of graph theories, planar, complete. So I think that'll do it. Thank you, everybody, for coming. We will be in touch. There's another meeting tomorrow at the same time. And check your emails to find out the subject. Every day, there's a different subject for a live lesson that we're teaching. Have a wonderful day, everybody. Thank you so much for coming. And thank you so much, Rabia Liaquat.
Thank you. Thank you so much.
You can, I think, I'm going to go ahead and let everybody unmute yourself. You can unmute and say bye. And then we'll leave in about 15 seconds.
Bye.
Bye. Thank you.
Bye.
Bye.
Bye.